Chemistry, Unit 3, AOS 2, LeChat's principle. In this session, we will talk about how LeChat's principle happens when a change is applied to equilibrium system and how this is represented in concentration versus time graph. Okay. So, reviewing the definition of a dynamic equilibrium. So, at equilibrium, both reactions are still occurring. The reaction ends but does not stop. How does reaction end? That is when concentrations of reactants and products stays the same. Okay, so it is equal rates for forward and reverse reactions. At equilibrium, the ratio, numerical ratio of concentrations of products over reactants is defined as the equilibrium constant. The value of the constant indicates the extent of reaction at equilibrium. So when Kc is large, it means the forward reaction is almost complete. And when Kc is small, it means the backward reaction is almost complete and forward reaction is almost non-existent. So here we got to introduce a new definition that is called the position of equilibrium. That is the relative amounts of reactants and products at equilibrium. That is called the position of equilibrium. So we said that at equilibrium, the rates are equal, but concentrations or amount, they do not equal to each other. So the position of equilibrium for different reactions will be different. It really depends on a particular reaction. Now, LeChat's principle. It describes when an equilibrium is subjected to a change, the system will adjust itself to partially oppose the effect of the change. What it means is that when you apply a change to an equilibrium system, so that it's no longer at equilibrium, then a net reaction will occur that partially counteracts the effect of the change. So the system will establish or reach a new equilibrium. So for example, if an equilibrium has already been established and you change the system in a way that, for example, you can change the system by adding one of the reactants, then the system will partially counteract the effects of the change. What's the effect of change? Added reactants. So the system will react in a way that consumes more of the reactants so as to reach a new equilibrium. Now let's look closer. There are different ways we could change the position of equilibrium to make it no longer equal. Okay? So we could add or remove a reactant or product. We could change pressure by changing the volume, or change concentration by diluting it, or change the temperature. Okay. Here's an example of when we added reactant. The reaction occurs is nitrogen reacting with hydrogen to produce ammonia. And this reaction has already reached equilibrium. Then, without changing the volume, we added extra nitrogen. Okay. The immediate effect to the system is that the forward reaction rate will spike, okay, due to an increased concentration of one of the reactants. From collision theory, we know that increased concentration of one of the reactants will increase the frequency of successful collisions. Therefore, a net forward reaction will occur due to the increased concentration. Okay? So on this rate versus time graph, we see that initially the system were at equilibrium. That is, the rates of the forward reaction and back reactions are equal. Then you added extra nitrogen. So the concentration of nitrogen increased, then the rate of forward reactions suddenly also increase. Yeah? Okay. But once the forward reaction instantly increases, increased forward reaction will consume the nitrogen that was being added. So this is how the system counteracts the change to the equilibrium system. Okay? So the forward reaction spikes, and then as nitrogen is being consumed, the forward reaction gradually declines. The rate declines. Okay. On the other hand, backward reaction rate catches up because the forward reactions increased. You also increase the product that's being there. Okay, so you produced more ammonia. Therefore, backward reaction, that is the decomposition of ammonia, also gradually catches up. And then there will be a moment when the system reaches a new equilibrium, that is, forward reaction rate equals backward reaction rate again. However, from this graph, you'll be able to identify that the new equilibrium is different from the old one because both the forward reaction rate, backward reaction rates are higher than before. Okay, which makes sense because you added one of the component. Of course, it will boost both the reaction rate, right? The forward reaction and backward reaction always affect each other at the same time. Okay, so new equilibrium, higher rate, and this is how system is partially changed. Okay. So from a concentration versus time graph, we can look more clearly. We can see more clearly how the system partially counteracts it. Okay, so you can see here that the nitrogen concentration spikes as a result of you adding extra nitrogen, but it will gradually decreases because the system will push you back. But it doesn't decrease to its original level. It decreases but still remains at a slightly higher level. This is what we mean by partially opposing it. Okay? And if you look at hydrogen, you'd realize that hydrogen actually is being sacrificed by this change, right? Although it was not manually added or removed, but because a net forward reaction will consume hydrogen as well, that's why concentration of hydrogen will also decrease, and they also decrease by their stoichiometry ratio. The amount of change in nitrogen will be a third of the amount of change in concentration for hydrogen. Okay? So overall, if we look at it macroscopically, when nitrogen was added, the system responds by having a net forward reaction so as to consume more nitrogen. However, the nitrogen concentration does not go back to the original one. It will go back a little bit but stays higher. And this is what we mean by the system partially oppose the effect of the change. If we look at LeChat's principle from a rate point of view, we'd notice that all of the changes that we could make to the equilibrium system will result in an uneven change in the forward or backward reaction rate. Okay? So when we added reactants, we would change the rate of forward reaction without changing the backward reaction. Or sometimes when we change the pressure, we will also affect either the forward reaction or the backward reaction, but there will be uneven effect. Okay? So therefore, this uneven effect will shift equilibrium position. However, at the center of an equilibrium is a reversible reaction. So the change in forward reaction will affect and result in a change in backward reaction, or vice versa. So this kind of interaction is what we see the system respond by compromising to a new equilibrium.